All right, now I'm recording. Okay, so we are talking about section 3.2, Rolle's theorem and MVT, mean value theorem. So Rolle, 17th century. Let f be a function that satisfies the following three hypotheses. So f has to be continuous, f has to be differentiable, and if those two things are satisfied and f of a equals f of b, then there is some number c, x equals c, on that interval between a and b such that the derivative equals 0. Okay? So, Justin, did you have another question for me, or was that is your hand up from the last?
Oh, how do I put it down?
Oh, just click on it again, or I can clear it for you. Here we go, I'll just do that. All right. All right, so I'm picturing like somebody stuck with their hand up like for all of class, like in real life. Okay, so this is what this looks like. Okay, here's the general gist of this, because sometimes all of these sentences and notation are, a little bit overwhelming. So f has to be continuous, f is differentiable, and f of a has to equal f of b. So that just means that if f of a equals f of b, then that means that the y values are the same. All right, that's all that means. The y values are the same. So they're on the same length. So you have, let's say this is a right here. And so therefore this would be a comma f of a. Like that, okay? And then if I have b over here, then this point right here would be b comma f of b. So they just have to be at the same height. That's what that means. So if we're continuous and differentiable, well, that just means that it has to be a nice smooth curve where it's all connected. You're not going to have any like holes or asymptotes or pointy edges or anything like that. So you can make anything you want. So we just have to start here and end here. So this could go like this and like that. Anything, as long as it's smooth and it's continuous. That's going to be satisfying 1 and 2. Okay. Now we have to be continuous on a closed interval. So these have to be closed, but differentiable on an open interval. Now, the reason that there's a difference there, it's a very subtle difference, but it's important. And that's because in order to be differentiable, you have to have a little bit of space on either side of the point to be able to make sure that the derivative from the left-hand side equals the derivative from the right-hand side. So if we use an open interval, then that excludes the endpoints. And we all know that you can't take a derivative on an endpoint. So that's why this has to be an open interval right here. Okay, little subtle difference, but something you should note, okay? And then these y values have to be the same, so they have to be at the same height. And so Rolle said, if that is the case, then there must be some x value, c, okay, maybe I'll put it right here, where in between a and b, such that the derivative at c is 0. So that just means that this tangent line has a slope of 0. And the example that I drew actually has more than one c. Rolle's guarantees that there exists at least one. But this one, you could have one right here. I could put one right here. We'll call that C2. That would be a spot where the derivative would be 0. And then if we said this was C3, here's another spot where the derivative equals 0. Okay? So basically, Rolle's theorem says if you start at a certain y value, and then you loop up and down or whatever in between, and you end at that same y value, well, whatever goes up must come back down, right? So therefore, there's going to be a spot where the derivative is exactly 0, okay? Here's some examples that are much more basic than what I drew, but also demonstrate Rolle's theorem. So you could have a flat line. So here's f of A, here is f of B, and then there's lots of c's. There's actually an infinite number of c values where the derivative is going to be 0. Okay, he listed a couple of them right here, but you got a lot of them. This is the one where what goes up must come down. This totally is an example of this. So if you start here at f of A and you go up and you have to end at the same height as f of A, right here, f of B, well, if we went up, then we got to come back down to that same height. Therefore, there's a spot in the middle somewhere where it's going to be a derivative or a tangent line with a 0 slope. Okay. Here's 2 more. Same idea. This one goes up, dips way down, and it has to end at the same y value that you started at. So this is the f of A, and here's the f of B. These have to be at the same height. So therefore, somewhere along the line, you must have had to have a maximum, and this one also has a minimum where the derivative equals 0. Okay, and then the last one, you don't have to go up, you could go down and then come back up to the same height. F of A equals f of B. So therefore, there had to be a spot where the derivative is 0. Okay? That's Rolle's theorem. All right. Any questions on that? All righty. Okay, let's flip over to the next page. So now we're going to apply Rolle's theorem algebraically. So you have this function f of x equals x to the 4th minus 2x squared. We're on a closed interval from -2 to 2, and we need to determine first if Rolle's theorem applies. So to do that, you have a checklist, 1, 2, 3. The first thing is f continuous on the closed interval from A to B? That's a yes or a no. Is f differentiable on the open interval from A to B? And the third question is f of A equal to f of B? Okay. So when you're asked to see if Rolle's theorem applies, you have to ask yourself those 3 questions right off the bat. If the answer is no to just one of those, then you abandon the question and you say, Rolle's theorem does not apply, therefore, I can't get the answer this way, okay? Can't find what you're looking for. So sorry. So let's look at it. Is f continuous on the closed interval from A to B? So knowing what you know about functions and given this interval, is the answer to that yes or no?
Yes.
Thank you. Good. That's a yes. Number 2, is f differentiable? Can we take the derivative on the closed interval, the open interval from A to B?
Yeah.
Yeah, absolutely. We can take the derivative everywhere. This is just going to be a polynomial, 4th degree polynomial. It's smooth, continuous. Now, this is the part we got to do a little bit of work. So we need to think, all right, is f of A equal to f of B? So this is A and this is B. So we actually need to do some calculations here. So f of -2 would be -2 to the 4th power minus 2 to the, minus 2 times -2 to the 2nd power. And then we need to do f of 2 to the 4th power minus 2 times 2 to the 2nd power. So you can do this super fast. Like you can determine an answer to this super fast on whether or not they're going to be equal if you know your powers of exponents, okay? So you got a negative number to the 4th power and then another negative number to the 2nd power. Is that going to be equal to a positive number to the 4th power minus some, you know, multiplication here, but that same positive number to the 2nd power? Will they be equal to each other?
Yes.
Yeah, yes, they will. Whatever this is, I don't know what this is, but they are going to be equal to each other. Okay, so yes, Rolle's theorem applies. Okay, so if so, find the values of x equals c that is guaranteed by the theorem. So the thing that's guaranteed by the theorem is that there is some x value that when you take the derivative, it's going to be 0. So you need to now take the derivative of f of x. So what will be the derivative of x to the 4th minus 2x squared?
Uh, 4x to the 3rd minus 4x.
Yeah, good. You're going to set that equal to 0. So take out a GCF, take out a 4x. You're left with x squared minus 1. We could keep factoring this. That's a difference of 2 squares, right? So 4x, x plus 1, x minus 1. Okay. So you're going to have 4x equals 0, x plus 1 equals 0, x minus 1 equals 0. So 0, negative 1, and positive 1. Okay. And we go back up and make sure that we have answered everything. Okay. So find the values x of equals c, the guaranteed theorem. Yep, we found it. So at x equals 0, at x equals negative 1, and at x equals 1, the derivative equals 0. So what does that mean in relation to this like chapter? That means that you could have maxes and mins at those spots. So now that we've actually done this, let's open up a tab of Desmos and see what the graph looks like. Or if you want to grab your graphing calculator, you could do that also. So what do we have here? X to the 4th minus 2x squared. Yeah, so that's a 4th degree polynomial. Make it big here. And so we are on the closed interval from -2 to 2. And we have 3 spots. Remember those 3 spots that we just found algebraically? 0, -1, and 1. Here they are. 0, there's a spot where the derivative would be nice and flat. That would be 0. At +1, the derivative would be 0. The slope of the tangent line would be 0. And right here at -1, the slope would be 0. So that makes sense with our graph. And we just did that all algebraically without having to rely on the graph. All right, so let's move on. So after Rolle, Lagrange came up with, he kind of added on to this a little bit. And he actually came up with the mean value theorem, which is really cool. Mean value theorem is like major superstar here with like calculus. Okay, so it starts out with the same idea as Rolle, only not quite as picky as Rolle. The only thing that you have to make sure is like criteria that has to be set is that f has to be continuous on the closed interval and f has to be differentiable on the open interval. Okay, That's the only two things that you have to satisfy with mean value theorem. And so if that is the case, then you are guaranteed that the derivative at some value C is going to be equal to this formula right here. So some of you may recognize that formula. I hope all of you recognize it. This is your like geometry slope formula, okay? F of B minus F of A all over B minus A. If you want to think of this as like an application problem, like your particle motion that you just had to do the flip grid on, this represents average velocity. This represents instantaneous velocity. I say that now because I'm trying to get you ready for when we do some application problems with this. Geometrically, down here, what does this mean? The slope of the tangent line will end up being equal to the slope of the secant line. So here's a picture. If you have some continuous graph from A to B, this would be the secant line to that graph. This other line would be the tangent line. So remember, if this is A, this point right here is A comma F of A. If this is B, this point right here is B comma F of B, right? If I want to know the slope of this line, I got to do y2 minus y1 all over x2 minus x1, right? Which is basically slope of the secant line, f of b minus f of a all over b minus a. Okay? So mean value theorem is saying, all right, if I take these 2 points and I find the slope of the line that I would get when you connect those points, there's gotta be a spot somewhere on this curve where the slope of the tangent line is gonna be exactly identical to the slope of this line, okay? The tangent line is occurring at C. Remember, the slope of a tangent line is the slope at just one point. So that's the derivative. So the slope of the tangent, that equals f prime of C. That's the beautiful thing about a derivative. It gives you a slope with just one point, okay? Otherwise, we have to use the old geometry formula for slope, and that requires 2 points. So mean value theorem is saying that somewhere along this curve, these slopes are going to be equal to each other. Somewhere in a physics problem, the average velocity of an object, of a trajectory, of anything moving is going to be the same as an instantaneous velocity, okay? A speed or a velocity at a certain point. So this second diagram right here is a lot more sophisticated, but it's the same, it's the exact same process. It's just a fancier looking graph. You take the endpoints. Remember, if this is A, this point right here is A comma F of A. You take this point right here. If this is B, then this is B comma F of B. If I connect those 2 points, I come up with a secant line. The reason it's called a secant line is because it crosses through the graph. That's why, okay? So if I needed to find the slope of this secant line, I would have to do y2 minus y1 all over x2 minus x1, which would be this formula right here. So mean value theorem is saying that, all right, if this secant line has a particular slope, there's at least one spot where I can find that same slope for the tangent line. And in this particular example, there's two. There's a spot right here and there's a spot right here where these are all going to have the same slope. They're all going to be parallel to each other. It's kind of a lot to wrap your mind around, but also it's like the more you think about it, the more hopefully it makes sense. So any questions about that? It's too early to know if you even have a question, right? It's like, okay, all right, so let's actually jump in. And if you want to like take a screenshot of this, especially if you don't have the printout of the notes, like, I don't know where to put that. I guess so the mean value theorem is right there. Take a screenshot so that you have it and then you can like pull it up and look at it when you need it. Okay. Alrighty, I'm moving on. Let's jump in here and do example number 2. See how this works. So determine if the mean value theorem applies, and if it does, find the values guaranteed by the theorem. So this is how this works. MVT, you only have to ask yourself 2 questions for this one, not quite as picky as Rolls. Is f of x continuous on the closed interval from A to B? And the second question is f of x differentiable on the open interval from A to B? So you have x cubed minus x. That's a polynomial. They're all nice and smooth. There's no like asymptotes. You don't have any corners, none of that stuff going on there. So it is continuous, and we do have a closed interval. So that's a yes. We just talked about how it's so nice and smooth and continuous. So it's definitely differentiable on the open interval. So that's a yes. Okay. So MVT does apply. So now, knowing that, we are guaranteed that there is some C value. They use C because they don't want to keep using X over and over again. Okay, C is like a particular X value such that the derivative at that point is equal to the slope of the secant line using the endpoints. So when you do this, you use the endpoints, the slope. Okay. All right, so this side requires us to do the derivative. So what is the derivative of x cubed minus x? Good, 3x squared minus 1 equals. Now, over here, we got to do a little plugging in. And so this is going to be f of 2 minus f of 0 all over 2 minus 0. So can somebody tell me what f of 2 is?
6.
Thanks. 6. And then f of 0, that's 0. All over 2 minus 0. So this is going to come out to be 3. 3. So 3x squared minus 1 equals 3. I think I'll just add 1. So we'll add 1. 3x squared equals 4. We need to solve this for x. Okay. Divide by 3. So x squared equals 4/3. Take the square root, and that's going to be like x equals. Now, when you take a square root, when you're solving an equation, you have to remember the plus and the minus, okay? Plus, minus. If you're graphing a square root, it's just the positive square root. But when you're solving an equation, you got to remember the plus minus. So this is going to be, let's see, plus or minus 2 over root 3, okay? you can leave that radical in the denominator. Calculus doesn't care if you have a radical in the denominator, okay? Some of you are probably cringing right now because you don't like seeing that radical in the denominator. You do not have to rationalize that, okay? All right, some of you are relieved because you hate rationalizing the denominator. So either way, hopefully you're happy. So that's it. So what is that saying? That means that we're guaranteed at these spots. So at x equals positive 2 over root 3 and x equals negative 2 over root 3, the slope of the secant line is going to be the same as the slope of the tangent line. So that's kind of way out there. Let's actually look at it on a graph. I'm hoping Desmos is going to be nice to us and like graph it the way I want it to, so it'll look good. So x cubed minus x. Okay, there's your picture. We are only on the interval from 0 to 2. 0 to 2. So I am going to zoom it in here. Whoa, that's a little bit too much. All right, so there we go. 0 to 2. Okay. So zoom out a little bit, just a little. I'm trying to get my 2 value to like show up for us. There we are, right there. So here and here. All right. So if I plot 0, 0, that was one of our points. And I plot 2, 6. Okay, so you got purple point, you got the green point. If I were to connect those with a line, I'd get a secant line, right? So let's see, if I connect those 2 points, that would be over 2 and up 6, right? So that's 3x. Yeah, there we go. So there's that secant line right there. Okay, see how the slope of it is 3? All right, now let's go back to the paper here. We had 2 other spots. X equals 2 over the square root of 3. And this is the part where like, I hope Desmos, I hope it cooperates. So let's see here. This would be 2 over the square root of 3, comma, I want to plot that point. Let's see, if I put that in, what would be the y value of that? 2 over the square root of 3 cubed. I'm putting, what am I doing right now? I'm putting that number into the original function so that we can get a point on the curve at our x value. Okay. Okay, so, that's ugly, but oh well, we'll take it. So 0.3849, well, that's good enough. 0.3849, we'll just go to 4 decimal places. And then the other point would be -2 over the square root of 3, okay, comma, let's see here, if I put a negative sign, what's all gonna happen here? Not much. -3 point. Yeah, -3 point, or 0.3, sorry, 0.3849. Okay, so see my little red dot and my little green dot right there? Now, we have to, I don't have any other points, and I'm not connecting those dots, okay? These represent the points on the curve that have a tangent line that would be parallel to this secant line. So I don't think I can graph that. I wonder if I could. Oh, well, not, I'll have to think about that later. Actually, let me just try something. If I do y prime, does that recognize that? It does not. Nope, it does not. Okay, so anyway, picture what the tangent line would look like right here, if you can. Little tiny tangent line. It's gonna have a positive slope that's fairly steep. It's actually gonna have a slope of 3. And then right here, if you can picture another tangent line, that is also gonna have a slope that's fairly steep. It's actually gonna have a slope of 3 also. So these would be the two spots on the curve that would create tangent lines that would be parallel to this. Okay. Okay. So that was our little visual for that. All right, back to the notes. All right, so example 3 is asking you to do the same thing here with mean value theorem. All right, just a slightly different equation that we get to use our calculator to help find the zeros of. So let's see first if it satisfies the conditions. The first question is f of x continuous on the closed interval? Sure, it's continuous. That's just a polynomial. So yes. And the second thing is f of x differentiable on the open interval from a to b? Yeah, that's just a polynomial. You can take the derivative anywhere on a polynomial. So that's a yes too. Okay. All right, so now we know then we are guaranteed that the derivative at some c value is going to be equal to the slope of the secant line using the endpoints. So somebody, can you tell me what the derivative of that function is? Good, thank you. Jasmine's here in class today, so she gave us the answer. And then over here, we are doing the slope of the secant line. So we're doing f of 2 minus f of negative 1 all over 2 minus negative 1. So can somebody tell me f of 2?
Um, 16.
16. Don't forget to subtract.
Do that 14.
14, there we go, good. Minus, how about f of negative 1? What's that going to come out to be? Negative 1? All over 2, let's see, chop, chop, that'll be 3. So 15, right? 15 over 3, 5. All right, so that means that this equals 5. So 3x squared plus 4x minus 1 equals 5. That's quadratic. We are going to set it equal to 0. So 3x squared plus 4x, subtract 5, minus 6 equals 0. Must be that doesn't factor very nicely, which is why we're allowed to use our calculator for this. So we need to find the roots for that. I'm just going to use Desmos since I have it open already. That'll be, and so I'm clear all these out. It's too much. All right, so 3x squared plus 4x minus 6. All right, where is that crossing the x-axis? Looks like negative 2.23 and positive 0.897. Okay, and that's all we're asked to find. We're asked to determine all the numbers c, so that's the x values. So x equals negative 2.23. Ooh.
Hold on,
wait
Miss
a sec.
Ngadi.
Yeah.
The f of negative 1 is 2.
Oh, is this 2?
I think it's supposed to be 2.
Okay.
I think. Hold on, let me.
Can somebody else confirm that? I'm just going along with what you guys are saying because I have the answer key next to me. Let's see. -1 cubed is -1 plus -1 squared would be 1, so 2. And then minus -1 like that. So
Yeah, it's 2.
yeah, that is 2. Okay, that's okay. So this will be 6. Oh goodness, let's see what will happen there. So what will this be? 12 on the top? Yeah. And this will be 4. Check me, you guys, okay? Because when I start making changes, then I don't know if I'm right. So that's 4. So I'm going to subtract 4 from both sides, which is going to make this -5. Which is an easy fix. Slight modification here. Put a little 5 in there. Now let's see, what are our roots? -2.12 and 0.786. So, does anybody have any comments about either of those answers? Anybody notice anything about those? They look good to you? Look all right? What's our interval that we're given for this problem? Oops. What's our interval?
-1 to 2.
Yeah, -1 to 2. That means that's all we can work with. So this answer right here, we gotta throw that out, right? -2.12 is not in our interval that we're working with. So throw that one out. Only take the 0.786. Okay. So just those little things, right? Be super observant. Any questions so far? So basically what you're doing is you're checking for continuity. You're checking for differentiability. If both of those answers are yes, then you're on to the next step, which means you're taking the derivative and then plugging your endpoints into a slope formula, okay? That's the whole name of the game here. So example 4, determine if MDT applies on this interval. If so, find the values guaranteed. So here we are, polynomial. So is f of x continuous? A lot of my students are like, do I have to write this down every time? Yes, you do, because when you write it down, it helps you remember it. If you don't write it down, you will not remember it as well. It solidifies it when you make yourself write that question every time. So anyway, the answer is yes. And then, is this differentiable on the open interval? Yes.
How do you tell if a function is differentiable again?
Okay, good question. So all polynomials are differentiable because they are smooth and like smooth curves that are continuous. You basically have to rely on looking at the graph. If you see vertical asymptotes, if you see pointy corners like an absolute value function or like a piecewise function that has like jump discontinuities and stuff like that. What would be another example? Oh, if you have like a cusp, like x to the 2/3, remember how that one looks like that? That is not differentiable right there on that corner point. So that's how you tell, okay? All other polynomials, like things like this, that's gonna be differentiable, okay? If all else fails, graph it, okay? If it's a complicated graph, just, try to and if you're not allowed to use a calculator or something like that, which right now that is not the case, you have all of your resources available to you right now all the time. So I would look at the graph. And otherwise, if you didn't have a calculator, you would have to start like doing an X and Y table and plotting some points and stuff. So that's how you tell. So this is good. So we're gonna do the derivative equal to the slope of the secant line. Okay. All right, so the derivative is 3x squared minus 6x plus 2. Your endpoints are 0 and 3, so f of 3 minus f of 0 all over 3 minus 0. What is f of 3? F of 3?
Shouldn't it be like 6?
What'd you get?
Shouldn't it be just like 6 because x
Yeah.
to the third power to
Yeah. 6. Good. And then f of 0 is 0. 3 minus 0, so 2. So 3x squared minus 6x plus 2 equals 2. That's quadratic, so we need to get it set equal to 0. So 3x squared minus 6x, subtract the 2's, equals 0. Take out a 3x, right? So this would be x minus 2 equals 0. So 3x equals 0. X minus 2 equals 0. So x equals 2. And this is just going to be x equals 0. So x equals 0 and x equals 2. Now, both of those answers look pretty good. 0 and 2. But here's the problem with this one. Even though you could argue that 0 is in the closed interval, we can't have 0 as an answer because you have to remember what these answers represent. These answers represent x values that you would create a tangent line on, okay? So let me say that again. When you get these answers, they represent the x coordinate where you would draw a tangent line. I cannot draw a tangent line at 0 for this example because 0 is the end point of this interval. So there would not be, like, we have to be differentiable on the open interval. So we cannot include 0 as a possible x coordinate, okay? So once again, when you get an answer that is one of your endpoints, you have to throw it out because you can't draw a tangent line on an endpoint. When they give you this interval, you have to think of the graph, only the piece of the graph that is including this interval. You can't assume that you have the whole graph. It's only that little chunk from 0 to 3. And you can't put a tangent line on an endpoint. So you have to throw this answer out and you only take 2. 2 is fine because our interval is from 0 to 3 and 2 is like right in the middle, pretty much of that, close to the middle. So that's an okay answer. All right. Any questions? Okie doke. Well, rounding out the very end here. So example 5. For the following functions, determine if MVT applies. If so, find the value of C guaranteed by the theorem. All right, here we go. So number 1 is f of, why do I keep writing if? I don't know. Is f of x continuous on the closed interval? Yes
No.
or no?
No.
No, you're right. Why?
There's like a vertical asymptote, I think, at x equals 1.
Very good. We have a vertical asymptote at x equals 1. Excellent. So, like I said before, as soon as you get a no, you're done. Like, so therefore, MVT does not apply. Next. So how about this one? You have g of x equals x to the 2/3. You're on the interval from -3 to 3. So first question, is f of x continuous on the closed interval?
Yes.
There it is. Very good. Is f of x differentiable on the open interval from a to b?
No,
Right. Why?
I guess.
Because it was one of the examples where it seems like the answer is going to be no.
Is it
All
the
right.
co-
X to the 2/3 is that cusp problem that looks like this. Like if you graph x to the 2/3, that's what you see. All right.
I knew that. I was
There
just
you go.
testing to see if
Of course you did. Exactly. Making me a better teacher. So the answer is no, not differentiable at 0. Cusps at 0, MVT does not apply. Okay. Perfect. Nice. All right, let's move on to example 6. Holy cow, there's a lot of words in this one. All right, here we go. So, Corpy's sarcasm is coming through. I can tell. You can tell by the smile on the pumpkin here. All right, the calculus cops have set up their elaborate speed trap on a busy, stretchy stretch of road. A suspected pumpkin farmer who uses the road daily to haul his pumpkins to market is suspected of chronic speeding well beyond the posted limit of 55 miles per hour. The calculus cops aim to finally ticket this unlawful transporter of seasonal gourds. The calculus cops set up 5 miles apart from each other, each parked furtively behind a piece of scenery. Calculus cop A spots the farmer with his jalopy loaded down with would-be jack-o'-lanterns. As the farmer passes cop A, he is clocked at a paltry 50 miles an hour. Cop A could have sworn the farmer waves at him as he drives by. Cop A immediately radios calculus cop B 5 miles down the road, whereby cop A starts his timer. 4 minutes later, cop B clocks the farmer cruising by at only 55 miles an hour. Okay. He clearly sees the farmer wave at him with a giant grin that would make a jack-o'-lantern jealous. After a quick calculation on his field-issued TI 88.5 calculator, he pulls out with his lights on to issue a speeding ticket to the ornery pumpkin farmer. For what speed can calculus cop B ticket the farmer? Would this ticket hold up in a court of law? Why or why not? All right, so you know this is a mean value theorem problem because it's in the notes, right? So you have to ask yourself, first of all, how are we going to use mean value theorem and does it even apply? So f of x is the speed for this problem. Is speed continuous on a closed interval from A to B in this problem. So point A would be the initial spot, and then point B would be 5 miles down the road. Is speed continuous? Yes or no?
Yes.
Yes, sure is. So you may think your car can jump from like 50 miles an hour to 70, but it's got to go through all of the speeds in between. So yes, it is continuous. All right, the second thing, f of x is the speed. Is speed differentiable on an open interval from A to B? So is speed a smooth continuous curve?
Yes.
Yes, it is. You can't make like sudden jumps in speed. There's no vertical asymptotes with speed. So yes, so mean value theorem does apply here. So what does mean value theorem state? That in this case, instantaneous speed equals the average speed at some point along this guy's travels 5 miles down this road. Okay. All right. So let's go back and read this again. Okay. So the cops set up 5 miles away from each other. So you got cop A. I don't know how I would draw this. Let's see. You've got like cop A right here, and then 5 miles down the road is cop B. So if this is 0, this would be 5. B equals 5. Okay. Five miles in between these two. When he goes by cop A, okay, when the farmer drives by cop A, he's going how fast? 50. Yeah, 50. So we'll say his speed is, we'll say 50 is right there. So he's going 50 miles an hour. So this represents distance, and this represents speed. Okay. So speed is your y-axis, distance is your x-axis, just so that we can like plot this. So 5 miles down the road, the guy does the radar gun on him and clocks him at 55 miles an hour. Oh, I guess it's not completely level. It's slightly higher, isn't it? Slightly higher. But remember, this is not Rolle's theorem, so they don't have to be the same height. Remember, MVT doesn't require that the y values be on the same level, only Rolle's theorem. So it's okay that this is 55. So now he's going 55 miles an hour. So mean value theorem says that if he starts at 50 miles an hour and he ends at 55 miles an hour, if I were to connect those 2 points, this point here would be 0, 55. This point right here would be 5, 55, right? 5 miles down the road, so 5, 55. So that average speed would be 55 minus 50 all over x2 minus x1, 5 minus 0. Well, actually, this isn't average speed, is it? This would be like speed divided by distance, which would be speed divided by distance. Distance equals rate times time. So what would that be? Just time, wouldn't it? If distance equals rate times time, and I have rate divided by distance, what would that give me? Rate divided by distance. See, divide by t. So distance over time equals rate. And then if I divide by t, that would be, I'm sorry, if I divide by d on both sides, where's my physics people? So 1 over t equals rate divided by distance. So this is just giving me it's giving me the reciprocal of time actually for this answer. So this would be 5/5, which would be 1. So that would not represent average speed, would it? Because that wouldn't make sense. 1 mile per hour, that's going to represent our time. Okay, so regardless of that, I guess my graph is not so good. So we can say, we can still use mean value theorem for this. We just don't need to do all the calculations. We can just think about conceptually what's going on here. So if he is clocked at 50 miles an hour, I guess we don't have to do the slope formula because we already have the actual speed. We need to do, he gets clocked at 50 miles an hour. And then 5 miles down the road, he gets clocked at 55 miles an hour. So what would be like the average speed for this between 50 and 55? Like 52.5. So the question is, can he get a speeding ticket? Is there any information in this problem that would warrant a speeding ticket?
No.
He traveled 5 miles in only 4 minutes, though, so he had to have been going over 6.
Ah, good eyes. That's right. They did say 4 minutes. Yeah, 5 miles in 4 minutes. So that's where I can do my distance equals rate times time. So if distance equals rate times time, and he went 5 miles in 4 minutes, all right, I got to change. So we're in minutes and he's going like, we're doing miles per hour here, but I got minutes. So 4 minutes would be what out of an hour? 4 minutes equals blank hours. So that would be 4/1 minutes. I want to get minutes to cancel out. So 60, no. What do I want to do here? 1 hour is 60 minutes. I want to I want to divide by 60, right? Good gracious, don't tell Ms. Beasley. Woof. All right, here we go. So we got to get the minutes to go away. So 1 hour, 60 minutes. So 4/60 is 1/15, right? You with me? Did I lose you a long time ago?
Yeah.
Did you walk away? Okay, so this needs to be 1/15. Because if we're talking miles per hour up here in the word problem, I can't put minutes in for the time when I do this. So 4 minutes is 1/15 hours. So get the rate by itself by multiplying by 15 on both sides. So 5 times 15. Five times 15, anybody?
75.
75. So he is actually going, he actually at some point had to be going well over 55 miles an hour in order to get from cop A to cop B in only 4 minutes.
I would go off if cops ever did this to me.
This is I don't think any of them are taking the time to do this kind of math, but that's kind of cool. So even though he started at 50 miles an hour and he ended at 55, since he got to his destination in such a short amount of time, there must have been a time when he was going more than 50 miles an hour in order to take up, like, get that distance that he had to get to in 4 minutes. Interesting. I guess we kind of used mean value theorem, but kind of used this information much more than that. All right. Okay, last one, example number 7. Let f of x be a function that is differentiable for all x. Suppose that f of 0 equals -3, and the derivative of f is less than or equal to 5 for all values of x. How large can f of 2 possibly be? All right, so this is just doing mean value theorem. So you need f prime of x equals f of b minus f of a all over b minus a. All right. So we know that we're given 0. So that is one of your endpoints. You are looking for f of 2. So that is your other endpoint. That's how you pull the information out of the problem. This is the first endpoint. That is the second endpoint. We know that this is going to be less than or equal to 5. So if you want to, like, because since we have an inequality here, you have to do this less than or equal to 5 part right here in the equation. If it helps you, rewrite your mean value theorem equation using the equal sign on this side and the f prime of x like that. That might help. Okay. It's really up to you, to be honest. All right. Maybe that makes it worse. Maybe we should keep it on the other side. This derivative has to be less than or equal to 5. So does that help if we put it there? Or should we keep it over here? I think we're okay. Would that make sense if we did this, or should we put it on the other side? If the derivative is less than or equal to 5, the derivative, no, sorry, let's keep it on the other side, because otherwise it's saying it's greater than or equal to 5 the other way. So this should be less than or equal to 5. Let me look that up. So in the meantime, you can put the 2 and the 0 in for the a and the b. So this would become f of 2. This would become f of 0. And then this would be 2 minus 0. And then I'm going to look at my notes, other notes. Okay. All right, I'm going to go with that. I can't quite see it yet, but I didn't see it in my other notes. And if I have to change it, I'll send you a message. But I think we're okay with this. The way I read this, I think we're good. So you would put f of 0 in right here. So this would be 5 is less than or equal to f of 2, which we don't know what that is. We're solving for that, minus f of 0, which is -3, all over 2. So this would become 5 is less than or equal to f of 2 plus 3 all over 2. Multiply both sides by 2. So 10 is less than or equal to f of 2 plus 3. Subtract 3 from both sides. 7 is less than or equal to f of 2. And now that I look at it, it needs to be on the other side. I was right the first time. Oh my goodness, I'm sorry, you guys. I shouldn't have second guessed myself. So this should have been over here. Otherwise, our answer doesn't make sense. So this, basically, you're going to switch places. F of 2 is less than or equal to 7. So how large can f of 2 be? F of 2 can be at most 7 in order to satisfy those equations. Okay, now for this one, suppose that f of 5 equals 2, so that's one of your values, and 1 is the other value. So since 5 is bigger, this is your B, this 1 right here is your A. So f prime of x equals f of B minus f of A all over B minus A. I'm going to fill in what I know before I mess with this inequality. So f of 5 minus f of 1 all over 5 minus 1. F of 5 is 2. We don't know what f of 1 is. That's what we're solving for. All over 5 minus 1, which is 4. We know that the derivative is greater than or equal to -3. So the derivative is greater than or equal to -3. So this has to be greater than or equal to -3. So can I do this? No, I think this has to go on the other side. So if you multiply by 4, that's going to be 2 minus f of 1 multiplied by 4 on both sides. So this would be greater than or equal to -12. Subtract 2 from both sides. So negative f of 1 is greater than or equal to -14. Yeah, now it's going to make sense. Divide by -1, and when you divide by -1, you're going to flip this sign. So f of 1 has to be less than or equal to +14. So what is the largest possible value of f of 1? The largest the f of 1 can be is at most 14. Get rid of this over here. Okay. All right, I apologize. Those inequalities, just like, I think I overthink them way too much. So for example 7, these kind of problems, you're just using mean value theorem and plugging in for the derivative. I think it's safe to say that we can always put the inequality on the right-hand side. I think you're good. I can't think of any exceptions to that, but I'll try to look up a nicer way to explain that. So meanwhile, that's the end of these notes. That's all of section 3.2. And so probably for the next couple of days, I'm just going to take questions. Like tomorrow, we'll do breakout sessions and you can ask me questions on the homework. Same thing with Thursday. I was going to teach 3.3, but I think I'll slow it down because you're getting a lot of material right now to digest. So we'll just do 3.1 and 3.2 this week. Wednesday and Thursday will be days where you ask questions. Friday will be asynchronous, and you have an AP classroom assignment on Friday that you need to complete. So yeah, that's about it. The bell's gonna ring here in about 2 minutes. Send me a message if you get stuck on anything. Work on those flip grids. If you can't get them to upload, just do like just do a YouTube video and send it to me. I really wanted to have another summative grade, and I think that's a nice way for you to demonstrate what you know. So, all right, everybody, I'll let you go. Thanks for sticking with me. See you later.